Hello wonderful person, this is Anton, and today we're talking about Venus. Now Venus is not a planet we normally talk a lot about, mostly because whenever we found out that it was relatively hot and somewhat hellish there, we kind of lost interest in trying to colonize it. Even though technically it should be the most interesting object to us because it's a lot closer in mass and even in composition to Earth than Mars is. But still, it's just too hot and we don't really know how to get rid of that heat. This is what we believe Venus may have looked like billions of years ago when it very likely had ocean. We'd still believe that Venus was very Earth-like in the beginning, and we believe it probably looked something like this. Mostly because of the fact that it's extremely similar to Earth in density. It has water that we've detected escaping from within. We also detected a lot of CO2 obviously, and a lot of the similarities resemble our planet Earth, but as if basically transitioned from a relatively habitable world to a world filled with CO2 that's completely uncontrolled, creating a tremendously large greenhouse effect. Now, today we're talking about a study that analyzed this idea of Venus having water, and when they ran the simulations using tidal inversion software from the Oregon State University that's often used to try to calculate the amount of tides and also the energy produced by tides. It's actually a very complex software that's used pretty regularly by people studying the oceans here on Earth. They realized that, well, if Venus had oceans, and if Venus had a certain depth of an ocean, there's a very high chance that it would most likely cause Venus to lose those oceans and become what it is today. This paper that you can find in the description below is an analysis of various tidal effects that Venus would have experienced if it had a liquid ocean of various types of depths based on the topography of Venus that was then used to calculate what kind of a shape the ocean of Venus would have. And the results were quite interesting. Now, these are not necessarily conclusive results, but based on the simulation and based on the topography, what the scientists discovered is that within only a few million years, Venus, or at least the surface of Venus, would probably look like this. In other words, because of the effects that it gets from the sun, because of these tidal effects, it's very likely it would transform into what it is today relatively quickly. Now let's discuss this in a little bit more detail because it's actually kind of interesting. So first of all, we know that on our own planet, which is by the way this, except that I'm basically upside down here, the tidal effects we get for the most part are coming from both the sun and the moon. And the moon is actually responsible for over 2 times more tidal effects than the sun is. Mostly because Earth is farther away from the sun than Venus. But on Venus, it receives about 2.67 times more tidal effects from the sun than Earth. So here the tidal effects would be quite more dramatic, but at the same time only a little bit more dramatic than the effects from the moon. At the same time, just having a dry surface like this is not enough to have any tidal effects. However, today we know that it's very likely that the surface of Venus is covered with so much thick layers of CO2 that underneath all of this CO2 that we have here, there is a layer that acts as a kind of a supercritical gas. In other words, it's a gas that sort of acts like a liquid and is responsible for changing the rotation of the planet. But we're not entirely sure if this gas was always there. It's assumed today that it was not always like this. On our planet, and I guess pretty much on every planet that has liquid water, the tidal effects are usually caused by the water, which of course makes sense because when we say tides, we often refer to the level of water. But the water itself causes other things. And when it comes to tides, this is normally how it's interpreted. So the gravitational effects from the moon create this kind of a tidal bulge right here on 2 sides of the planet. And that's because the gravity sort of stretches the planet, creating a slightly taller or slightly higher level of water here than here. But the thing is, because the planet also rotates, the tidal bulge actually gets moved a little bit in front of Earth. And so the real bulge is under an angle. And because of this, the fact here is that First of all, this transfers some of the energy to the moon's orbit and pushes it away from us. So moon is constantly moving farther and farther away. It used to be a lot closer to us, now it's farther, and will be a lot farther in the next few billion years. But at the same time, this force also pulls back on our own planet, slowing it down a little bit. And so today we know that the planet used to orbit a lot faster. As a matter of fact, when the dinosaurs were walking Earth, the single day on Earth was approximately 20 hours long. And when Moon and Earth were just created, a single day was about 6 hours long. So the planet used to spin about 4 times faster. And eventually, every object that has tides becomes tidally locked. So sort of like if we were to look at Pluto and its partner Charon right here, these are tidally locked objects. What this means is that they're always facing each other with the same side. So as Pluto and Charon orbit around one another, they're always facing each other. And this happens because eventually, because of tides, things become tidally locked. This is true for every major object that has any kind of a liquid ocean on the surface or underneath. So for example, every major moon like Ganymede, Io, Europa and so on, all of them are tidally locked as well. And it's very likely that this tidal lock occurred because they have liquid oceans inside. And so pretty much every single object with liquid water or with an ocean on the surface is going to at some point become tidally locked or at least slow its rotation. So this is very likely what happened to Venus. Because this particular study, when they assumed that there was ocean here, which let's just create this really quickly by giving Venus a liquid ocean right here. So in this case, depending on the depth of the ocean, it would most likely cause different types of energy from tidal forces. And when they ran the simulations, they found very different results, but some of those results were quite dramatic. So even though today, if you were to basically add oceans to Venus, because of its slow rotation, the tidal effects would be about 0.15 gigawatt of energy in total, which is something like 5,000 or 6,000 times less than what it is on Earth. If Venus was rotating faster, so maybe something closer to planet Earth, where a single day takes a single day, in that particular case, the energy from the tides would be dramatically higher. And they've discovered that some of those tides might have been just as high as they are on Earth. So in other words, it would produce approximately 600 gigawatts of energy, which when they ran the simulation gave the planet so much drag because of the tidal effects that it would start slowing down quite a lot. Some of their calculations suggested that it could lose as much as 72 days per million years. In other words, within about 10 million years, it could have slowed down to a crawl that it has today and basically become tidally locked. Now, those were some of the more extreme versions with a very specific depth of an ocean. I think it was about 600 meters on average. But if the oceans were deeper or more shallow, it may have not had as much effect. But it doesn't change the fact that the tidal effect would still be powerful enough to slow down the planet within about a billion years. And if this planet suddenly slowed down like it did right here, it would then be basically exposed to the solar radiation 24/7. And if it becomes tidally locked like this, it's very likely that it's going to lose any kind of magnetosphere it might have here. Because we believe magnetosphere is actually created by the rotation of the planet, or at least partially created by that, lack of rotation here would kill magnetosphere. Without magnetosphere, all of this ocean would start evaporating like crazy. Venus would most likely start losing tremendous amounts of water really quickly. It would escape into the atmosphere as hydrogen and oxygen, which we still detect even today, eventually becoming barren like this. And then this would start the cycle of CO2 release, and the planet would become hotter and hotter pretty much every single year, with CO2 eventually covering the entire surface, causing really high greenhouse effects and superheating the planet to the temperature that it has today. And so this is one of the major discoveries in this particular paper that suggests that if Venus had ocean in the beginning, this ocean would most likely kill the existence of water on the planet. In other words, it's kind of like doomed if you do, doomed if you don't. If Venus had water, it would most likely lose all of it almost instantly. And if it didn't have water, then it had this really thick atmosphere that probably did the same. Now, interestingly, today, Venus doesn't really have a tidal lock anymore. As a matter of fact, it has something called retrograde rotation. In other words, it actually spins in the opposite direction of other planets. And we believe this is formed by this thick atmosphere. So the atmosphere that it currently has, if you were to look underneath it, and by the way, you'd probably see something that looks like this, but what you would see here and what you would actually feel here would feel like liquid. Because this lower level of atmosphere here has so much pressure and so much temperature that the carbon dioxide that's here starts acting like liquid. It literally flows across the surface of Venus. And this flow also creates tides as well. So there's a very unusual, very interesting CO2 tide on the surface that's causing Venusian rotation to change again. And in the last few billion years, it acquired a kind of a balance where it literally has an equilibrium between the tidal lock caused initially by the sun itself and by the water that may have existed here, and the atmospheric tides that are caused by the heating of the atmosphere by the sun and by the very unusual properties of supercritical carbon dioxide that's on the surface of Venus. And we've recently actually become quite interested in the so-called supercritical CO2 because it also might be the source of very clean energy. But I'm going to talk about this in another video. Nevertheless, the main discovery in this paper is that no matter what Venus used to have in the beginning here, it most likely, even if it was a much faster planet, which it probably was, it would have lost the spin despite anything. It would have lost it if it had thick atmosphere. It would have also lost it if it had the liquid ocean because of the tidal effects from the sun and because it's relatively close to the sun compared to planet Earth. Even though Venus was probably habitable like you see on the screen right here, eventually this actually destroyed the ocean itself. So it's kind of ironic in a sense that these tidal effects basically caused the planet to lose the ocean. What's important about this study is that it allows us to now understand how this could happen on other planets, specifically exoplanets. Because of the approach that this particular paper took, we now can potentially study what happened on other planets. Like, for example, if we go to TRAPPIST-1, with its 7 terrestrial worlds, today we believe that many of these worlds are maybe water worlds. But if they are water worlds, it's very likely that many of them also became tidally locked, and it's very likely that they may have suffered the same fate as Venus. So it's possible that pretty much every world that becomes tidally locked becomes similar to Venus. So this is something that we need to investigate a little bit more, because one day it will hopefully help us find a planet that's not like Venus, not like Mars, but a planet that's like Earth. If we understand how these effects evolve and how all of this changes with time, we'll be able to find this beautiful Earth 2.0. But remember, until that happens, we still only have one Earth. Only this Earth. I guess you can call it Earth 1.0. So we do have to take care of this planet a little bit better than we do right now. Because unless we find somewhere else to live, there is just no other hope for us. Anyway, on that somewhat sour note, thank you for watching. Hopefully you enjoyed this video, and if you did, don't forget to subscribe. Share this video with someone who enjoys learning about space and sciences and wants to learn more about the universe in general. And maybe even consider supporting this channel on Patreon, because it does help me quite a lot. I'll see you tomorrow. Space out, and as always, bye bye.